Hello, this is the Critical Design Review presentation for Senior Design 2, Group 3. We are doing a laser beam characterizer. I am Zachary Andreessen. I am a photonics student and electrical engineering major. We also have Thomas Cunningham, who is an electrical engineering major, and Lindsay Smith, who is a computer engineer. This project is sponsored by Lockheed Martin. So part of the motivation for this project is that the team that I work with at Lockheed Martin does a lot of model matching and system characterization. So a lot of it entails measurement of laser systems. So this system is designed to simplify a lot of this process and automate it so that the laser that we're using, we can have it better characterized, which improves our models and improves our systems. So the four main things that we want to measure in the system are the wavelength, the polarization, the divergence, and the beam quality of the laser. And so these correspond to our basic goals. For measuring polarization, we hope to do this with a quarter wave plate and a fixed linear polarizer. By rotating the quarter wave plate and measuring power after the linear polarizer, we can extrapolate the Stokes parameters to measure the polarization. For the wavelength of laser beam, we can use a Michelson interferometer and a photodiode detector. For the divergence, we have a simple lens, and when we measure the width of the beam at the focus point of the lens, we can calculate the divergence from that measurement. And finally, from the m squared factor, when we have a long focal length lens, we can measure the width of the beam using a scanning slit detector at various points along the focus, and this will allow us to calculate the m squared factor of the laser beam. Aside from this, we also want it to be rather lightweight and also stay under budget and be really easy to use and user friendly. So these are our basic goals. And for our advanced goals, we want it to not only be useful for small powers, but also for very large powers as well. Because often in many systems, you have higher power lasers. So broadly, how we would do this is make sure our optics can meet this spec, but also have the option to add or remove ND filters into the system where needed in order to cut down power enough to be measurable. Additionally, we also want to have a broad range of input beam sizes because this allows us to measure a small beam that's like maybe 4 millimeters all the way up to a bigger beam that's like maybe 30 millimeters. So in order to do this, we want to have a lot of our optics be very big, and we're shooting for a minimum of 40 millimeters clear aperture on all of the necessary optics. And then aside from this, we also want to be able to detect, if possible, any potential errors in our measurement so that we can catch any mistakes. And then finally, for some of our stretch goals, we want to do a broad range of input wavelengths. So we want our components to be as achromatic as possible. And then to accompany this, we also want to be able to use our wavelength measurement to correct for any adjustments in any of our other measurements, for instance, the polarization measurement or the beam quality measurement. These things are dependent on wavelength. So we want to be able to use that measurement to correct our other measurements. And then finally, we also want to, if possible, to measure the waist size and location. These are other factors of the laser that can be helpful, but are not as helpful. And then we also want to, if possible, to allow for pulse lasers. The plan is mostly to accommodate for CW lasers only, but if possible, if we have time, we'll create the possibility for pulse lasers. And then lastly, we'll have the beam wavelength and polarization data. If possible, we want to report that live so that it's not just a simple one measurement system, but a continuous reading system. So here are some of our specifications. They're split up into the input beam specifications and the measurement specifications that we want. So for the input beam, I want to achieve a 1.2 to 2.1 micron range. Is the far IR region, or maybe not far IR, but not quite. It's higher than a lot of an IR region. Um, but also I want to have a broad range of input powers, like I said before. So minimum power between 1 to 50 milliwatts and maximum power 1 to 10 watts. So this is a pretty broad range. And then, like I said earlier, we also want to have a broad range of beam sizes. So we have 4 millimeters to 35 millimeters as our specs. And then for the measurement parameters, for the normalized Stokes parameters, we want to be within 5% for all 4 of the Stokes parameters. For the wavelength, we want to be within 10 nanometers, M squared factor within zero point 0.1, and beam divergence within plus or minus 10 microradians. And then for the total power, which is an additional measurement that we can do in the system, we want to be within 5% error. And you can see here we have the 3 parameters that are highlighted for the that we will be demoing. And then here we have our general work distribution. I'm the project lead, so I handle the optical alignment and as well as the optical system design and the photodiode selection. That's for the photonics part of things. For the electrical side of things, T will handle the MCU selection, design, the motors that will be used to automate all of these systems, as well as the power supplies. Uh, and for my part of engineering, I handle we have 2 transimpedance amplifiers in our system that I design. And then for the computer side of things, we have Lindsay, who will handle the GUI implementation, the communication, as well as the STM32, which we'll be using for our MCU and the website design. And here we have a basic layout of the optics of our system. So here we have, at the bottom, you can see that we have 2 irises. These are going to be used as a reference so that the user has an easy way to align the laser to our system. And then immediately after those 2 irises, we have our core to wave plate and linear polarizer that we can adjust to measure the polarization. This then leads into we have a long focal length lens, 812 millimeters, that we can use to redirect into our power meter. And on the power meter, you can see there that there's a little slit there. This is going to be a servo motor with a knife edge that we use to scan across the path of the beam. Allows us to recreate the beam profile that allows us to measure the beam width. And then in the path of the beam, right after that lens there is a movable mirror that we will be controlling with a servo motor that will allow us to do that wavelength measurement with the Michelson interferometer there.
Yeah, for the main electrical system, it's fairly simple. We're going to have the whole system supplied by a standard 12-volt DC wall adapter, which will then get split into 5 volts, which will supply the photodiode and power meter TIAs as well as the servo motors. Where the 3.3 regulator is solely to power the STM32. Um, they The 12 volt power will go directly into our stepper drivers, um, which I designed, and the whole system connects to a computer via USB interface.
For the STM32 programming language, we chose embedded C because it was uh gives us full low-level access to the STM peripherals like the ADC, DMA, and the timers. And it's best suited for the high sampling rate and FFT processing in our laser measurement system. For the GUI framework, we chose PySide 6 because it was a strong real-time plotting and professional UI capabilities, and also supports a modular design for multiple measurement plans like polarization and M squared. And it's widely used in scientific instruments and lab software. For the embedded software design, so the system, once it powers on, it will initialize the STM peripherals like the ADC, DMA, timers, motors, and USB. Then the firmware will wait for the measurement plan selection from the GUI. And once that measurement plan is selected, it configures the scan parameters and calibrates this whole system. And then we have a closed loop measurement process, which controls the stages and optics with the motion control. We have sensor data acquisition using ADC and DMA, and we have real-time signal processing. That process data is then streamed to the GUI for visualization, and any final beam parameters are computed and the system returns to idle. For the GUI interface software design, it is a central GUI for controlling the polarization, M-squared, divergence, and wavelength measurement plans. Its real-time data acquisition and plotting is then sent from the STM32. It contains dual operation modes consisting of a hardware mode and a simulator mode for testing and validation. It also has live visualization tools, including the beam profile, FFT, and polarization ellipse plots. And it's a modular pi-side 6 architecture enabling scalability and research-grade laser characterization workflow.
So for some of the optics hardware selection, some of the two main components that we were worried about was the splitter that we use for our microsync interferometer. For this one, we picked this part that has a very even 50-50 split. It's non-polarization based. It's a plate beam splitter that should have a even split across our wavelength range. So this was ideal for our application. And then we also had this power meter from Thor Labs. This power meter is ideal because not only does it have a broad power range due to its low responsivity, but it also is easy to integrate into our system because it's a simple photodiode that we can read with a TIA that we design.
There are two main contenders for microcontroller were the STM32, specifically the G4 series, and then the ESP32. We decided to go with the STM32 for its hardware superiority, um, especially on the ADC side, since we'll be taking these sensitive measurements from the photodiodes. It offers a very accurate and linear ADC, especially compared to the ESP, which is not known for its ADC quality. The STM32 also supports motor driving natively, as opposed to where the ESP, you have to download community libraries. It's very has native USB support, which is not really too much of a factor. ESP is very good in that too. And it's also appealing because it's one of the more industry recognized controllers, and just a very robust one overall. For the motors, we have a lot of different moving stages in this project, and we decided to go with stepper and servo motors, mainly due to the different accuracies they involve. For the quarter wave plate rotation is really key that we're able to get an accurate difference in angles, and so we decided to go with stepper since it allows for like with fractions of a degrees of rotation. For all the translations, which would be for the beam quality and for the Michelson, we decided to go with a ball screw driven by a stepper. It gives very accurate and precise stepping in linear range. And for the beam profiling slits with knife edges, opted to go with servos because you could control the absolute position a lot easier, and they have a fair we didn't need the full 360 degrees. And then for the mirror switching, we need to be able to reliably keep it out of the path of the beam, and the servos seem to be a good fit for that. For the power, like I said before, we opted to go with a 12-volt DC wall adapter. It's split into the 3.3 and 5. The 3.3 only supplies the microcontroller, which shouldn't exceed more than 200 microamps. The 5-volt has a little more demand. The TIAs don't require much of the servo motors. Under normal conditions, for not doing very much load, should only be around 10 to 50 milliamps. but the regulator is equipped to supply for higher like 2 to 3 amp stall currents if that happens. And for the 12-volt rail will directly connect to the stepper motors and to um, one of the TIA circuits. Um, for both the 3.3 and the 5, we decided to go with the LM 2679, which offers both of those voltages due to its high input voltage range and its relatively high current output. It's within, I think, 5 amps.
So for the Michelson photodiode, uh, there's a simple TIA that I designed here, with a 2K resistor in the feedback loop of the op amp. It's designed for a lot of flexibility, but this is the schematic and PCB layout for that. And then for the power meter TIA that is going to connect to that Thor Labs optical power meter, this one was a little bit more complicated because it requires a much broader range of powers. So since the responsivity of that is super low, uh, uh, there's a the current through it won't be super high, but there's still a broad range of currents that I need to account for. So in order to do that, I used this chip, which is a ADG1211 chip from Analog Devices. And it's basically just a voltage controlled switch. And I'm only using three of them, three of the four on this chip, but it's connected to three of the resistors in this feedback loop. And so by closing one of these switches, we can control the switch with our microcontroller. But by opening or closing the switch, we can control the gain of our TIA. That will allow us to accommodate for all of those that broad range of power that we need.
Controller schematic. Some of the basic elements are here, such as the external boot configuration and reset, but um, the rest of it was up to me to make. On the right side, you can see all of our breakout pins for all the GPIO we did not use in case we have something that gets upset during the project and we need to add something in a pinch. Um, on the left side, we have the 12-volt power, and then upper left, there is the USB with the diode protection and V-bus sensing. This is also going to be on the main PCB. You have four stepper driver connections that have the step and direction photo or no, Hey, I have optocouplers on them. Basically, the moral of the story. So that if anything comes back, our um, microcontroller will be protected. And then also have three connections for servo motors with their standard configuration. The layout is pretty straightforward. I gave myself plenty of space, um, but very connection focused. For the regulators, since the chips have the same layout, I just designed one board and checked that the components were all the same, which they are. Have a large diode, takes up most of the space, but it's designed to clip right into the main PCB. The stepper motor driver is made with a DRV8825. Um, it is straight from the data sheet. This is no different and is designed so that the pin layout matches what you can be standardly available online in case something happens.
So for some of our testing that we've done for this system yet, one of the things we've tested is the polarimeter design. Now, in this case, we didn't use motors, but we just manually rotated the quarter wave plate. And so these are the results we got. So I tested all sorts of polarization, vertical, horizontal, circular, linear, all sorts of stuff. Here are three of the results that we got. So for vertical polarization, you can see we got a very clear line, vertical, 45 degrees, same thing, very clear with only a slight degree of ellipticity. And then for circular, we saw a very nice little circle that we got there. Now for the interferometer testing, uh, this we also was able to test this in the lab. Uh, this was tested on an oscilloscope, not with our microcontroller, but it's the same idea of just sampling. And so for this, I used a Heaney laser simply for ease of alignment. And since the wavelength is smaller, the frequency will be higher. So since we're working in the IR region, it should be easier to read those signals with a longer wavelength. But with this, I simply moved the mirror at a constant speed and then extrapolated the dominant frequency of that signal in order to calculate the wavelength. And so we can see that at the sampling rate of the oscilloscope that I was using, of 1.25 gigasamples per second, I extrapolated 632.9 nanometers, only 0.1 nanometers off from the typical 633 nanometers of a Heaney laser. This is very good, even though this sampling rate is much higher. Even at lower sampling rates, you can see that it still works fairly well and will work for our with our designs.
For the STM ADC functionality, we are using a Nucleo G474RE dev board. And so far we have tested two measurement plans, an FFT measurement and a power meter reading. So for the FFT measurement plan, we are using a combination of the ADC and DMA, and a timer is used to trigger the ADC at a fixed sampling rate, which we have at 100K right now. The DMA is continuously filled in a circular buffer with signal samples from the function generator we've used. That function generator is at a 1K frequency. In the results shown in the left picture, we can see a strong spectral spike at the input frequency, which indicates that the FFT is correctly identifying the dominant periodic component of the waveform. And that clean spike with low noise floor means that the signal is stable and well sampled. And any slight offset from the exact frequency is mainly due to the FFT resolution limits or the timer-derived sampling rate accuracy rather than actual error in the algorithm. For the power meter measurement plan, we've used the same ADC DMA timer triggered acquisition, which then converts the incoming voltage into digital values and averages them to get a stable measurement of optical power. The result shown in the right picture shows a smooth voltage trend corresponding to changes in beam power as the servo scans the beam across the detector. And any small fluctuations in the signal are mainly due to ADC noise or power meter noise, while the overall slope of the voltage curve reflects the cumulative power profile. And then taking that derivative on the bottom graph, it reveals the beam profile.
This is some of our administrative content. This is our bill of materials. We have a $7,000 budget, and so far with our plans, we're staying within it. And then some of our future plans for this, we've had some delays with getting some of our hardware, but once we've received all of it, we plan to build and test all our PCBs and fully set up and align the optical system. We'll confirm that all of this will work with our STM32 ADC, as well as getting our motor controls accurate, and then just testing all of our, see that we can actually get measurements. And then finally, after that, once we know that we can get measurements, we'll make sure that we calibrate everything so that it can be as accurate as possible.